blame it. We'll blame it on.
That's where Emily learned to be a. So.
No. And we found your stability, instability stuff went away, and you got results and stuff.
Yeah.
Yeah. So hopefully everybody's doing that. I mean, I'll be around. I got a 3 for 11 to. I'll be around like after 1 if you have any other additional questions and stuff. And then, what's that?
Started today.
Yes, yeah, get started. Hopefully everybody started it at this point, right? So we're going to jump back into multiple degree freedom systems. I have a gift for you.
Homework?
Homework number 7.
What does that do?
Due Monday.
I have it due. Well, what do I have? What do I have?
Push it off a ways. I got 11.
Was that Monday? Or is that Friday?
It's Friday.
Yeah, move it to Monday. I forgot Amanda requested it due on Monday.
Monday is Thanksgiving, so let's put it back to Thanksgiving. That's when That's that Thanksgiving week.
No, it's not.
No, so we got one more week.
There's one more week. Yeah, the Monday after that, yeah. By the end of the day, you actually should have enough stuff to go through it all. Okay, and this MATLAB, right? This is MATLAB stuff. How you're going to do this? So it's due. So change the date to 14th, 11/14, the due date. 11/14. Okay. So we're in the middle of this stuff, right? Refresh your memory, right? We wrote this thing out as a in matrix notation. This is a matrix type problem. We set up our matrix problem like this. This just comes from equilibrium. We set it out to mu double dot plus ku is equal to p, right? That is a system of differential equations. You can't solve this because it's linked through the stiffness matrix. Those off-diagonal terms, those k terms, off-diagonal terms, link what's happening with the displacement of 1 with what's happening with the displacement of 2. So we need another way of solving this. So we're going to use modal analysis where we kind of break it in different modes, solve it, and bring it back, right? Because there's no easy way to do it. So we're going to do the modal analysis stuff. We talked about assembling a stiffness matrix. We talked about different formulations of stiffnesses and mass matrices, right? But we're going to mainly focus on like a shear building. And in fact, I don't think we go above like a 3-story shear building. Right, and so we were talking about free vibration, which means what, Ethan?
No, that's it.
Couldn't tell you.
Which means there's no extra load. I can't wait till 2 years from now when I teach this class again. I'm like, this guy named Ethan, he was at the right before the exam, he said, "What's free vibration?"
You might get some answers that like, what is free
Yeah. That's a very good question. That's a very good question. Right. Oh,
Did you elaborate?
I hit the wrong.
Inspiring story, it really is.
Yep, that's right. And you recovered.
I recovered.
Yep. So then we worked our way through this and kind of assumed the form of a solution, worked our way through, and then what popped out of it was this classic eigenvalue problem, right? And where it is you have a matrix multiplied by a vector, it's the same as equal to a scalar multiplied by that same vector. This lambda and that vector are properties of A, and you get as many lambdas and x's as you do, in our case, the degrees of freedom. However big, if A is an n by n, you get n eigenvalues and n eigenvectors. Okay? And so then we worked our way through there. We said, well, in this particular problem, what it ends up being, the eigenvalues are the circular natural frequency squared, and then the eigenvectors that you get from this matrix right here are the mode shapes. Okay, and then hopefully that's refreshing your memory here a little bit. So we came back to this example that kind of demonstrates this concept, right? So we just 2-degree of freedom system like this. You're doing in your homework, you're doing a 3-degree freedom system. So basically, you're doing this problem as you go through your homework with different initial displacements. So what you do is you assemble your mass matrix, assemble your stiffness matrix, and then you ask for the eigenvalues and eigenvectors. The eigenvectors, we get 0.5 and 1, and we get -1 and 1, and those are the shapes. So 0.5 and 1. So this is floor 1, that's floor 2. So it's how much floor 1 moves over and how much floor 2 moves over. That's the shape, and then that gets multiplied. As we're going to be talking about today, what this Q function is, but it is a function that's oscillating. It's the vibrations that's happening. It's that oscillations. This thing has a period of which comes from our omega squared, right? You take the square root of that, and then you do 2 pi over the square root of that, and then it gives you what that period is. So this thing has a period of 0.89 seconds. And so this time-changing part gets multiplied by this vector, which just makes it look like it's vibrating back and forth, right? And the same thing with this one. This is -1 and 1, and then that just gets multiplied by the scalar function. And so if it's positive, it looks like that. If it's negative, it looks like that. And if it's 0, it looks like that. So that you can kind of see how that thing would vibrate like that, would oscillate like that. Okay? Any questions about that? Right? The thing that we haven't talked about yet is what the hell is this Q? Right? Q is a time-changing part. We keep saying that. It comes from a single degree of freedom system, but we'll get to that in a second. That's what we're covering today, is what that is. Right? I made a sick GIF for you just to. Oh yeah, this guy. Just kind of illustrated again. This is what we're aiming for. This is for a 3 degree of freedom system. This actually is your homework. Right? You don't have to make these sick ass graphs like I did, but there's the extra credit part is making it animate. You don't have to do it, you know. I made mine like shear floor, so you could just do like you did on the last one, which I haven't given you credit for yet, but like just the oscillations of the nodes if you want, right? But then this is mode shape 1 in this particular thing, right? And that's the shape. So that phi, that shape function would be, it would be 3 positive numbers, right? And that's what's off to the right. That's what the red that you see is that shape. And then this is the Q, and the Q is going back and forth. This is the period of that, right there. And then so that one oscillates back and forth slow because it has a large period. So it's just that shape that just keeps getting modified like that. This is mode shape 2, which has 1 node. So it has 2 things off to one. Actually, in this case, it has 1 off to one side, 1 0, and 1 off to the other side. And that's what that shape looks like. That shape just gets multiplied by this Q, and that Q has a very small period, or a smaller period, so it goes faster. It vibrates a little bit faster. And then this next one is mode 3, where it has it's positive, negative, positive is what that shape is, and then that gets multiplied by this, and that has a smaller frequency, so it vibrates even faster. The overall answer is this, plus this, plus this, and that's what you get right there. So this is maybe like your intuition would say, oh yeah, this thing was pulled back both to the left and then let go, and then it started oscillating, and so the first one whips by and it catches the second floor, and the second floor kind of whips back, and they're all interacting together. And then how we model that is just with these 3 separate modes. It's a really clever way of solving these things. It's really neat. Right? And then, like I said before, if you came in and you excited this one, if you came in under the ground, for instance, and shook it, and you had the frequency match this mode 1 frequency, then you would see mode 1 pop out. You would see it. If you came down, you'd get resonance in this, and these other ones you wouldn't, so you would see this one. You come in and you shake this one at this frequency, you would see mode 2. And then, because you get resonance in mode 2, you come in this way, shake this one, you get resonance in mode 3. You can actually see these things. And that's exactly what's happening when that sugar or salt thrown on there is it's getting resonance in each one of those mode shapes, and then all that sugar's falling into the nodes, and you can kind of see what those mode shapes look like.
So are those
You see the
plots-
nodes of the mode shapes. You don't see the mode shapes. What's that?
Are those plots like just molecular floors then, or would you actually plot?
Yeah, no, so these down here, this is just what Q is doing. Q is going like this, and Q is getting multiplied by phi, and then phi has those floors in it. So that's a great question, James. You're paying attention, bro. Pay attention, right? So these are my phis, and that gets multiplied by Q. And then Q is this, right? So in that other example, Q is the advanced maneuver coming in, bro. Okay. Q is this part that you're asking about, and then Q is getting multiplied by the vector being like one of these guys for mode 2. This is obviously 2-4, but it's getting multiplied by that, and that's why it's
Different on each floor.
yeah, it's different on each floor. So the phis are the floors, Q is the time. Phis are the floors, Q are the time. Phis are the floor, Q are the time. You'll see it play out the more you do this. Literally, this is one of my favorite subjects to teach. It's so cool. It is so cool. It's cool. You look less than excited. Pumped up. You pumped up?
Oh,
I'm just gonna wait until the day before the homework started, and then you'll just go through the solution. I can just copy it down.
kind of like on Monday when I did that really quick. Yeah. Wednesday or whatever it was. Oh, you weren't there.
I was here.
Oh, you
but
were.
There's no reason to start it early if you're just gonna go through the answer. Well, I have to learn it.
Well, it was because I was based off of all the
My
people in my
troubles.
yeah your
All my
troubles. It's your fault for starting it early. Good point. I see your point. The reason I did that is because all of Jake's troubles, and he pointed out all these things that we didn't know, and then I learned it, and I was like, I should probably share this information. I should teach it.
Next time you do the homework, you could break it into like 2 parts, like do just like the ELF method or something, and then like knowledge
Yeah.
it better,
Yeah.
like just give it to
I
you.
think it, but listen, I think it worked out. I think everybody learned it.
Yes, but like
Worked out
for your
great.
grading even, you know, it's like really hard when everyone has different periods and different
Yeah.
stuff in their models, then you can't like have a baseline. to
Yeah.
compare to.
I usually grade homework based on how I feel about you. I just look at the names. I just look at the names, honestly. I just look at the names and say, yeah, I think James knows it. Yeah, or I freaking hate that James. He gets a 6. Just a gut feeling on how I feel about you. It's straight up judgment. Straight up judgment.
Sarcasm just brought himself
Homework
to be.
5's not
Yeah.
graded yet.
Today I'm gonna grade my dynamics exams based on what calculator they're using. just what it is. I said there were 2 solar powered calculators in dynamics this morning. 2 solar powered calculators. One guy had 2 TI-89s, and that guy's getting an A+. Extra credit. He's like, just in case one of them goes out. I was like, I would think that you just bring extra batteries, but he brings 2 straight up TI-89s to class. Just this one stopped working. Throw it away.
Oh, you bring the solar as the backup calculator.
Yep.
Should
Uh,
for being a troll, Harry.
Yeah. I was impressed. I'm not even mad. That's a smooth move, man. But two solar powered calculators in that class. I was like, dude,
2 TI-89 equals 1 in
just
Sky.
use the technology. Use it, man. It's awesome. It's a tool that you could use, right? Like, it's the same thing with guys that ride fixie bikes, you know? Like, you ever seen those guys? They're maybe not around here too much, but like in Seattle, there's a lot of people riding fixies, right? So there's no freewheel, there's no brakes. It's just the chain is connected. The front chain is connected to a fixed back rotor thing. There's no gears. Then if you want to brake, you have to slow down your pedaling, right? And kind of go the opposite. You want to get going again, you get it going. And if you're going fast, your feet are going because there's no freewheel, and it's like there's no reason for it. We have this new technology. It's called hub that spins and then gear changes. Like,
You just take your
it's engineering.
feet off the pedals and
Yes, I guess, right? Take your feet off the pedals and go.
Like smacked or something.
It's just, yeah, I agree. It's
Another
stupid.
reason-
It just if somebody uses a solar powered calculator. Same deal. It's stupid.
What if
There's a
was
tool.
Solar powered T89.
I'd be okay with that. It's not the solar power. It's not the solar power I have an issue with. Yeah. Oh, you one of those hippies that believes in climate change?
More batteries. More
That's
batteries.
good. I'm gonna freaking solar. You freaking hippie. Not in my class. Not in my class. Climate change. That's a good
More
one.
lithium ion.
Yeah. That's funny. And then check to see if they have rechargeable batteries. Dock them for that. Only disposable in here, bro.
You see
Alright.
the calculator I use on this exam in here?
What'd you use?
Solar powered FE calculator.
Really? Is that what you use? Is that your standard?
Yeah.
I'm gonna start docking you, bro.
Pure beauty.
I use my 84 and you're smart. The FE1 is at home.
It's
Okay.
actually more for.
I want to see what I say about this. So this is key to the.
It's got like plus minus multiply.
This is key to how this process works. Is this modal orthogonality? What does orthogonality mean?
Perpendicular.
Yeah.
Perpendicularity.
Well
Great.
said.
Great.
Well said.
Great. So what happens is this. This is, like I said, this is key to how the process works. Okay? If we take our phi function, our phi vector, right? You get as many phi vectors as you have degrees of freedom, right? So, there's in our case a 2 by 2, you'll be a phi 1 and a phi 2, okay? And then in your homework you have a phi 1, phi 2, and phi 3. Okay, you'll have 3 of those vectors. If I take one of them, and that t there is transposed, which means you flip it on its side. So if it's really rows then columns. You have 2 by 1, then you turn it into a 1 by 2. So instead of this way, you put it on its side. So if you put it on its side, multiply it by k, which is your overall stiffness matrix, and you multiply it by one of the other ones, right? Because I doesn't equal j in that case, then it's equal to 0. Okay? This is how we're decoupling the system. I'll show you in the next page how that works. But if this is the case where I does not equal j, what's that?
Tim tried to tell us 0 over 0 is 1. And now you're doing the same thing.
Why did it do that? Oh, okay, yeah, but then phi, so then same thing. The same thing will happen if you do the phi transpose m times phi j, you get 0, okay? And that's just, you can show it. Part of your homework, I say, show me that this works, okay? Show me that this happens. And right, so you'll make your phi factors, and then you'll do this, and you'll show that it equals 0 is all I want you to do, okay? And then, but then down here, if phi transpose k times phi, if these are equal to each other, the same one, they don't equal 0. Right? So only if they're not equal to each other. If I try to do mode shape 1 transpose times k times mode shape 2, I get 0. Okay? And then it's not, the k and the m have to be in there. Okay? Okay. Right. In this case, right? Same I. And these are all topics that are covered in the book. Okay? And then we broached this subject last time. That eigenvectors are not unique. Uh-oh, come on. Unique? Okay. They're not unique, and so they can be normalized in different ways. One way you could do it, so these are all the same. These are all the same eigenvectors. One way is you make the top floor 1. And there's really no right way to do it, but can make top row 1.
So top row.
Or top floor. Floor. I know, right? See, I always say that students make that mistake, but really it's me that makes the mistake. So you keep me in line there, but you're right. Top floor is equal to 1. That's one way you could do it. You could do the bottom row equal to 1 if you wanted to. You can make.
It's just the ratio that matters, right?
Yep, exactly. You can make largest value equal to 1. So the reason I mention this because certain things do that. I think that your calculator does one of these. I don't remember which one it is. The TI-89. Your calculator doesn't do it, but other people's calculator. I think a TI-89 makes the top. I think it makes the largest value equal to 1, right? The other one that we can do, that's just a couple different ways, is this one. And you're like, why would you do that? I'll show you kind of why you do that. But if you do, one way to normalize them is to make phi I transpose times the mass matrix times phi I equal to 1, and then if you do that, if you set that up equal to 1, then you can set phi I transpose k times phi ends up being omega 1 squared, omega I squared. That should be omega I squared.
And when you say I, that's just one of these.
Just one of them. Make one of them. Right. So if you do it for phi 1, you'll get omega 1. If you do it for phi 2, you get omega 2. Right. That's just a way of normalizing it. This is what MATLAB does. They look weird. If you remember, I showed you that example last time, and they looked kind of weird because they appear random. MATLAB does when you use eig k comma m. If you don't do I k comma m, it does something else. It normalizes them a different way. If you do I m to the negative 1k, then it gives you, it normalizes them a different way. But I'm going to recommend using the I k comma m. Right? And when you do that, it normalizes it, just like I said. It makes the phi transpose m times phi equal to 1, and the phi transpose k times phi equal to omega squared. Right? So I would recommend just, if you're using MATLAB, just use the I k comma m, and then it'll be normalized that way. They'll look weird. They appear weird, and they appear somewhat random, but the ratios in between them are all what they're supposed to be.
So can you just solve it and then like divide it by?
You could, yeah, once you get it, yeah, that's right. And if you wanted to change it to the top floor equal to 1, you just divide all the numbers by that number divided, that initial number, so you get 1 for the top floor and then everything else. Yep. Yep. You could change them into whatever you want to after that. Okay. So, modal expansion of displacement. So this is kind of what, we need to put in a sum here. I forgot a sum. I know, it's the same, I just copied the equation down. Right? So this is kind of just one more look at it before we go on to the next one. So phi 1, right, for the 2 by 2, this is 0.5 and 1, right, for that example above. This is, Wait, all right, we'll make it. Times Q1, right, plus, negative 1, 1 times Q2 measured time. That's what U is equal to, right?
Q comma Q1.
Q1, Q2. Right? And so that Q1 again is doing this, right? It's some function which we haven't gotten to yet. Right? Q2 is another one, but it's going faster. Drop my pencil. Having issues now. This one's gonna go more rapid. Right. This is going along. Right. So this one right here is U. This is U, what we would call U1, and this one we call like U2 in that equation above, and they're vectors. Right. This is just kind of mathematically writing what we just saw in the previous demonstration, right? So this U1 right here doesn't mean floor 1 or floor 2. It means mode 1. It's U from mode 1. The floors come in when from this vector right here. That's what floor 1's doing. That's what floor 2 doing times that time changing part. So U1 is a vector as a function of time. U2 is a vector as a function of time. And then the overall solution is just add them all together. Okay. Okay, that's all. I just got to see that. That's so once you get this thing and you bring it back to the real world, you have to do this, right? So let's talk about what this. Let's kind of show you something. This next part, this is all me. The book doesn't do it this way. I do it this way because I saw this once and I was like, holy crap, this is sick. I think it's the best way to explain how this process works. I'm very proud of it. I feel like I need to write a book now because this works.
Or just a chapter.
Or a chapter. I'll submit it.
Just a paper.
What's that?
Just a paper.
Or just a paper. Maybe a paper. A paper saying, hey, think of it this way. Think of it this way. What's he doing? What's he doing, Dawson? Is he texting?
I'm
Snapchatting?
Looking up what about this stuff.
Really detailed.
about this stuff, yeah.
What exactly were we learning?
I'm just looking at, this stuff, bro. Okay.
Yeah.
So we're gonna write this thing in matrix notation, right? The whole thing in the full-on matrix notation. But I'm gonna introduce these guys. I don't know, I think we've used this a little bit. We've talked about this. We have talked about this. I'm gonna make a big matrix like this, which is, all these guys are, this is my phi factors. And what I mean by the lines there is just, I'm taking phi 1 and it's a stacked column. Phi 2 is a stacked column. Phi 3 is a stacked column. right? So you just take it, and that's what MATLAB returns us to it like this, right? It returns us big phi, right?
So phi one would be mode one.
Yep.
And then as you go down,
Yep.
it's floor one.
We have floor 1, floor 2, floor 3 for the shape for mode 1. Right. Yeah.
We made a joke in the office today. We were talking about big delta and little delta.
Yeah.
So little delta sounds like a rapper. You say big phi.
Big phi.
Big phi kind of sounds
It
like
does.
a rapper.
Dang right.
I think a good one does.
Is that what you were looking up? Right. Now, big omega squared. Big omega squared could be a nice wrapper, right? Big omega squared is my omega 1, 2, and 3 down the dike. So this is for a 3 by 3. I'm setting this up for a 3 by 3, just kind of for demonstration purposes. So big omega squared, and big phi. This is actually what MATLAB returns to you if you do it. I'm at. Yep. So actually, that's what you'd set it up in your code. You'll say this, right? You'll go. I mean, obviously, you're gonna have to call it something else, but you go. Oh. And you say like big phi. You can even call it big phi if you want, right? And then you call it big omega squared is equal to ig k comma m, right? Where those are matrices as well, right? But that's what your coding would literally say. I mean, I can't literally say it because you can make a variable big phi or capital. I do capital phi is what I usually do, and then that would be like big W capital W squared, right? Is equal to ik comma m. And what it does is it returns you those two vectors or those two matrices right there. It's actually structured in that fashion right there. Okay. I'm also what I'm gonna do with my q's, my q functions, I'm gonna stack them vertically like this. Make a new vector called q, which is my q1, q2, and q3 through qn down. In our case, it should be q1, q2, and q3. I'm gonna stack them that way, right? And then in MATLAB, actually, they're not just gonna be one thing, they're gonna be really long, right? Because T's got a bunch of numbers in it, right? So it's 0 through whatever you're looking for. So Q's gonna actually have, it's gonna have a bunch of time steps that way, but then they're gonna be stacked. That's gonna be Q1, it's gonna be Q2, it's gonna be Q3, right? But in this case, we just think of it as it's just a function of those things, okay? So when we just talked about to get what U is, we do the summation of phis times Q's. Another way to write that mathematically is just big phi times Q. So the way matrix math works, I'll speak very slowly for you, Hunter, here how this works, okay? The way it works, right? If I do big phi right there times Q stacked like that. So if you think, watch what it does, it goes, it does those Q1 times phi1, and then it goes over and goes, big phi 2, or that phi 2 times Q2, and there's gonna be Q3, and then it automatically sums them up for you, right? So this summation right here, you could just write it as big Q times, big phi times Q, right? When Q is a stacked thing like that. Okay. Same thing happens with accelerations. If I want accelerations, I can just do big phi times Q, like that. Everybody buy it? You with me? With me? Jockey got it? Right there? Okay, so you come down here. So here's our equation. Mu plus Ku is equal to 0, right? That's our equation of motion, right? And this is a coupled equation of motion because K has off-diagonal terms. It's linking, they're linked together, so it has off-diagonal terms. Can't solve it because of those off-diagonal terms. So what I'm gonna do is I'm gonna say, all right, this new substitution for U is equal to Q, big phi times Q, that guy right there. I'm gonna take those, I'm gonna put them in here. That's right there, right there. Right, so I just substituted U and U double dot, put the big phi times that. Then what I'm gonna do is I'm gonna pre-multiply everything by big phi transpose. That's what it does.
How'd you get Q double dot?
It's a derivative.
Nice.
It's the second derivative, actually. Let me try. I'm not paying attention right now. Pre-multiply by big phi, big phi t transpose. Right. So what was your question there?
How'd you get Q double dot?
I just took the second derivative of it. Big phi doesn't change with time. right? It's constant, so it comes out of that derivative, and then just q double, so it's just, it ends up being the second derivative of q. Yep. Q is the only thing changing with time. So I just took the second derivative of u, and it gave me that right up there. Okay, so you could do it right, this algebra, right? You could do everything, you could do anything you want to, as long as you do it to both sides of the equation. So we're gonna do that same thing to both. So I just pre-multiplied by big P transpose on both sides. Okay? We're gonna call this thing right here big M, right? Because these things happen, that's just big M, and this is just big K. We're just gonna call that. Okay? So we said, let's look at this term right here. Big phi transpose K times big phi. Right? Our big K term. So I'm gonna look at big K. Well, big K is just big phi transpose times this K matrix times